So, good evening, everyone. So, I will be discussing the assignment 3 previous year questions. So, in assignment 3, what are the topics? So, let me write down the topics for the assignment 3, which you will find the topics are same for this year's assignment also. Okay. This week's assignment is not very tough. You will be able to do it. Okay. If you understand some basics, so we will discuss those basics and then you will be able to do. Okay. So what are the topics for this week? So number one is open circuit test. Short circuit test of transformer. Okay, and then we will see efficiency. Okay, so in next week we will see maybe the voltage regulation, but in this week we will be only seeing the efficiency of the transformer. Okay, what is the efficiency formula and how it is related to open circuit short circuit test. Okay, so let us start. So we will be starting with the OC and this I'll be writing it as OC and this I'll be writing it as SC. Okay, so first, we will be discussing OC and SC test. So, what is the objective of this test? Okay, so the aim or aim or objective of conducting OC test and SC test on a transformer is to predict its performance, right? Is to predict its performance like efficiency, voltage regulation, all sorts of things. Okay. Efficiency, voltage regulation without actually loading the transformer. Okay. So without actually loading it. So basically what we do is so main objective is for performing this OC and SC test is to predict the performance of the transformer, okay, without actually loading it. So once you have the equivalent circuit parameters, you can basically study everything, okay. You can study the efficiency, you can study the voltage regulation and other performance characteristics of the transformer, okay. Now, basically what you do is like, as I said, equivalent circuit, right? Now, for getting the equivalent circuit parameters, OC and SC test is used. Okay. So, OC and SC test is used to get the equivalent circuit parameters. So, you can say in a very, what you say, informal language, the second statement. So in a very informal language, you can say that, okay, if someone asks you like, okay, what is OC and SC test? So you can informally say that, okay, the open circuit and short circuit test is used to get the equivalent circuit parameters, okay? But the formal answer, if suppose you go to any interview or something, you should tell that the objective of conducting this open circuit and short circuit test is to predict its performance characteristics like efficiency, voltage regulation without actually loading the transformer, okay. So So without actually basically giving the power supply to the transformer, how you can determine these performance things? That is the objective of the open circuit and short circuit test. But indirectly, for what you say, doing that performance study, you need to know the equivalent circuit parameters, which is determined using the OC and SC test. Okay. So now let us see one by one what is OC test. Okay. So OC test or open circuit test. Okay. So OC test. So these are very important statements. Okay. Like there are various things which I will be writing down in these statements. Okay. So listen carefully. So open circuit test is carried out at rated frequency and at rated voltage to determine the core loss. The core loss thus determined एक minute. Okay, I thought someone came. So I was writing that the core loss thus determined, like basically you do open circuit test at rated frequency. These lines, these are very important lines. Okay, this one, rated frequency and at rated voltage to determine core loss. Okay, this is the gist of the things, but I'm writing some more things, okay, which will clarify whatever I have written. Okay, so the core loss thus determined, okay, is then treated as constant. Okay, despite minor variations So the core loss thus determined is then treated as constant despite the minor variations. Okay, minor variations in frequency and voltage during actual operation. So one may say that why, like I'm saying that one may say that why we are carrying out this open circuit test at rated frequency and rated voltage. So that is the basic question, right? So let us see why we do that. Okay. So why we perform the open circuit test at rated voltage and rated frequency. Okay. So if you remember in the last class, we have seen that the what is your EMF equation of a transformer? So the EMF equation of a transformer is this root 2 pi F Bm and number of turns, right? Now these other things like number of turns and all this is constant. So what about Bm? Bm is proportional to E by F, is it not? So you can see that Bm is proportional to V by F. So you and we have seen the hysteresis loss and eddy current loss formulas also. We have seen that the eddy current loss formula is So basically core loss are of two types, eddy current loss and hysteresis loss. Okay, because this is a so in the eddy current loss, we have seen the formula in the last class. So you would have seen that it is proportional to bm square and f square. Okay, and what about hysteresis loss? Hysteresis loss is proportional to bm to the power of Steinmetz constant, which is taken from 1.5 to 2.5 or something, and then this into f. Okay, so you can see that there is bm and there is f. And what about bm? Bm is proportional to v by f. So that is why, so that we can determine the rated hysteresis loss and rated eddy current loss, because rated means ki, if we operate the machine at its rating, like suppose a machine is said to be rated to be 400 volt, 50 hertz, and all that. Okay, like suppose this is like this, a transformer is like 400 is to 1200 volt transformer, 50 hertz. Okay, so basically rated, or and some power rating is there like 5 kVA. Okay, so the rated, what you say, operating the machine at rated conditions means that you are applying 400 volt at the input, you are applying you are getting 1200 volts suppose at the output. So basically you are operating the primary and secondary windings at their full voltage capacity. So if you do that, what will be the hysteresis and eddy current loss or core loss? Okay, so एक minute, just let me remove this. Okay. Mm. Okay, now let me go here. So that is what is meant by rated. Okay, so rated means that you are operating the transformer at its full rating, like full primary voltage, full secondary voltage, the rated frequency. So in those conditions you will have some core loss, right? Now generally the machine is meant to be operated at its rated and rated voltage and full capacity, because in those conditions it gives its optimum performance. Okay, so it is said, right, you do not operate the machine in underrated and overrated values. You try to in general operate the machine at its rated values. Okay, so if you operate your machine at rated value, so what kind of core loss will you get? Okay, so core loss consists of hysteresis and eddy current loss. Now we have seen that the eddy current loss formula is proportional to bm square f square, and hysteresis loss formula is proportional to bm power k into f, and bm is proportional to v by f. So if we have to get this eddy current loss rated, hysteresis loss rated, so this bm also has to be rated, f also has to be rated. Okay, so in both the cases it both has to be rated. Okay, and when is bm rated? Bm is rated when you are operating at V rated and F rated. So that is why for open circuit test, because the main objective of the open circuit test is to determine the core loss. So to get the core loss at its rated values, okay, at the machine ratings, we carry out it at rated frequency and rated voltage. And once the core loss which is determined, it is, you will see that we will treat it as constant in various conditions. Okay, you will see that whether there is whether the machine is operated in underrated, under what a half load, full load. So half load, full load means ki current rating reduces, but generally we operate the machine at its rated value, rated voltage. Okay, rated voltage and rated frequency. Why? We have seen it in the last class. Why we operate the machine at rated voltage and rated frequency? Because otherwise the flux will saturate. Okay, so the flux is proportional to V by F. So if we are not operating at if we are not operating the machine at V rated and F rated, you will see that the machine, the flux can saturate. Okay, so to avoid that, we operate the machine most of the times at rated voltage and rated frequency. Okay, so the current can change. Current can become half. Current can become 75%, depending on the load. Okay, so the load determines how much current is drawn from the transformer, but the voltage and frequency is more or less constant in various conditions, and thus we treat the core loss as constant. Okay, so you will see that in various questions, you will see that whenever there is a half load, full load, still the core loss or iron loss will remain constant. Okay, now let us go to the another point related to open circuit test. Okay, so what is this other point? So OC test is carried out with instruments placed on low voltage side. So what I'm writing down is the procedure of open circuit test. Okay. While the voltage, high voltage side is left open. While the high voltage side is left open circuited. This is because, so why it is said that OC test is performed on low voltage side, not on high voltage side? What is the reason? You see, your main objective is to get the core loss at rated values, right? So you can perform the OC test even at the rated high voltage value, right? So why do we need to perform the OC test on the low voltage side only? So I will draw the diagram so you will understand what I am talking about. This is the general practice of doing the OC test. Okay. So this is how the equipments are placed. So as I said that the equipments are placed on the low voltage side. So this is your watt meter. Okay. So this is the watt meter. Now here we have the ammeter. Then this is your transformer. This is transformer low voltage side. We are putting the equipments on the low voltage side, and then we are having the high voltage side on this side. High voltage side is open circuited, as I said, and all the equipments like wattmeter for measuring the power, voltmeter for measuring the open circuited voltage, all this is kept on the input side or below voltage side. Okay. So these are the things which are measured from these meters. Okay. So we measure, so what we do, we connect a supply here. So we give a supply here. Okay. So this is a supply. So let me just draw a supply. So this supply basically, so this is a voltmeter. Okay. So this supply here is a rated frequency, as I discussed in the first line, rated voltage supply. Okay. So rated frequency, rated voltage we are giving. So we give low voltage rating. So if suppose this transformer is rated as 400 volt to 1200 volt. So on low voltage side, the rating is 400 volt. So you give 400 volt on the low voltage side while keeping the high voltage winding open. Okay. And then you measure the, so as you know, the voltmeter, this voltmeter will show 400 volt AC, right? The wattmeter you will get some reading, and then the current what you say, this ammeter will also give you some open no load current reading. Okay. So these readings you take, but the question is that why we are not doing this on the high voltage side, why on the low voltage side? Okay. Why it is said like, acha, this is a hard and fast rule that you should do it on the low voltage side. Okay. It is not a hard and fast rule, but there is a logical explanation for that, so I'll tell you. Okay. So in general, OC test is done on LV side because you will see that the arranging rated voltage supply okay at the low voltage level is easier. Okay. So that is the reason. Okay, that is one of the reasons. And another reason is that it is safer to operate at low voltage level, right? Because anyway you have to, so this is a 400, suppose for example this is a 400 volt 1200 volt supply. So as you know that in our homes you can easily get the, like in generally labs also, in our in yours, like what you say, laboratories, in your colleges, you will see that the 400-volt supply is available. Okay. Similarly, so that is why, so you can give a 400-volt supply easily to the low voltage side. 1200-volt supply is not available. Okay. So this is a very, what you say, logical explanation of why we generally do it on low voltage side. Also, it is, what you say, safer to operate, right? So if you are suppose giving 1200-volt here, it is a bit more dangerous, right, to give a 400-volt supply here. So that is that is another reason. Okay, so these are the reasons for which we do the OC test on low voltage side. Okay, so after that, and another thing is that since this no load current, we have seen that there is, in the current, in the primary current, there is a no load part, and then there is a, so you have seen this, right? I1 is equal to I0 plus I2 dash. Now since, because we are operating at we have put the high voltage winding open, so this I2 dash is 0. Okay, so the primary current is only this no load current. And also you will see that the no load current is limited to about 5% of the full value, or full current value, full load value. Okay, full rated value. You will see that the no load current is only 5% of the full load value. So so you will see that the copper loss, okay, I square R1 and I1 square R2 dash losses, okay, this copper losses are very small and can be neglected. Can be neglected. And thus the wattmeter reading, okay, the wattmeter reading thus represent the core loss. So it is said, right, that if you take the, if you do the open circuit test, you have placed this wattmeter, so you will see that this POC which it is measuring, this POC is nothing but the core loss, because this, you will see that this I square R1, I1 square R1, because I1 square R1 will become I naught square R1, and I naught is very small, 5% of the full load value. So that is why these copper losses can be neglected. Okay, they will become very small. So it is generally considered that the wattmeter reading does represent the core loss. Okay, so that is the reason. Also, so this is the thing. And another thing is that since this no load power factor is low, you will see that this no load power factor will come out to be 0 0.2, 0 0.3, like that. So since this no load power factor, okay, since the no load power factor is very low, okay, as I said, it is 0.25, 0.2, in that range, it is recommended that the low PF wattmeter is used. Okay, so you can go in your college laboratories and you will see that there are two types of wattmeter: low PF wattmeter and UPF wattmeter. Okay, so we will be using low PF wattmeter for taking the power reading in the open circuit test. Okay, so that low PF wattmeter should be used for OC test. Okay, so these lines, I have said so many lines on OC test, like there can be so many what you say, interview questions, so many theory questions in this NPTEL course, like it has, like most of the things related to OC test. Okay, now you will see that we will be measuring this VOC from this, you can see from this arrangement, we will be measuring VOC, POC and I naught. Okay, so so how we will determine the, what you say, this parameters, right, RC and JX5. So it is like this, that this is your R1, JX1, and then you have JX2 dash, R2 dash. So this is RCJXM. Okay. So we have considered that this no load current is very small, like it is 5% of full load current. Okay. Even in industries, people consider this, okay, when doing the open circuit test. So what they consider is that this drop I0 into R1JX1 can be neglected, okay. So it is basically like you are having this kind of arrangement, okay. So it can be neglected. So basically neglecting this drop. So you are having VOC rated, okay. You are having I0 and you are getting POC, which represents core loss, okay. Now after getting these things, how to calculate RC and XM, okay. So this is how you calculate RC and XM. So quick calculation will give you these values. So what are these values? So RC is VOC square by POC. Then number two is this, basically this, so here there are two ways you can do, okay. And then another way is this one, okay. So this is the more what you say practical way, okay, so which I am writing. This is having the, because this is parallel connection, remember, so you have to do it like this only, okay. This is the correct procedure. VOC by VOC I0, then your X phi or XM, okay, or XM becomes PC by tan phi 0, okay. Remember, this is a parallel connection. So if you do V by I is equal to Z, that will give you maybe wrong answer. So you have to go by this, okay. This will give you the exact answer. Now we will see the SC test. As we have seen the points for OC test, we will see the points, the important points for SC test also, okay. So what is this? So let us see. So here, how we connect the things. So this is the ammeter, okay. Here we have a variable voltage supply, like from an auto transformer, okay. This though we do experiments in the BTech labs, okay. So, okay. So this is the variable voltage supply. Then you have a wattmeter, okay. So you have a current coil and then you have a wattmeter like this, okay. So this is the wattmeter. Now here, so this wattmeter will give you PSC, okay. This will give you PSC. This current is ISC. This is the voltage. This is the voltage. Sorry. So this is the voltage VSC. And then you have the transformer winding like this. So this is high voltage side. This is low voltage side. And low voltage side is short circuited. Okay, so this is shorted. Short circuit. So this is the situation. So this variable voltage supply is given from the auto transformer. Now, SC test is carried out at rated current. To determine the full load copper loss. Okay, so that is the thing. Now, we do it. So basically from the short circuit test, we get the copper loss. Okay, so the main objective of the short circuit test is to determine the full load copper loss. Okay. Now, short circuit test, okay, is carried out with instruments placed on high voltage side, okay, while the low voltage side is short circuited. So that is the thing. Now, from the same logic, if you see, suppose this transformer is, suppose this is high voltage side, 400 volt is to 200 volt. Suppose 5 kVA transformer. So on this side, the rated current on the high voltage side will come out to be 5000 by 400. And on this side, the current rating will come out to be 5000 by 200. Is it not? So what is this current? This current is 12.5 and this current is 25. So this is 12.5 to 25. So you can clearly see that on the high voltage side, the rated current is 12.5 ampere, and on the low voltage side, the current rating is more, which is 25 ampere. So because we do the short circuit test at the rated current, so that is why we do it on the high voltage side, because on the high voltage side the current rating is less and it is safer to operate, and all those same explanation. Okay, it is easier to get this much of current, 12.5 ampere. It is a less current. It is a, so among these two rated currents, this current one is the less current, so it is easier to arrange voltage supply which can supply this much of current. Okay, remember that all the voltage supplies cannot give you 25 ampere, 30 ampere like that. Okay, otherwise the fuses will blow off, MCB will what you say, get open in the home and all those things. There are various protective circuits, right? So that is why it is easier to arrange a what you say, um, low rating current voltage source. So that is why the short circuit test is done on the high voltage side. Okay, so now you will see the equivalent circuit diagram. So if you see, and see, another thing is that because you will see that for getting, when you have short circuited the low voltage side and you are giving the voltage supply till you get the rated current ISC here. So suppose ISC is here 12.5 ampere. So you will increase the auto transformer very slowly. You will see that the 12.5 ampere will begin to flow at only 5 to 10% of rated voltage. So you will see that, okay, this is 400 volts. So at only what you say 40 volt or like 35, 30, 40 volt, you will start to get 12.5 ampere because this is short circuited. Okay. So, because since the voltage required to circulate rated current at short circuit is in the range of 5% to 10% of the rated voltage. Okay. Of the rated voltage. So the core loss at such a low voltage is ignored. Okay. So the core loss at such a low voltage sorry, is ignored. Okay, and therefore the wattmeter reading in this case, okay, represents full rated copper loss if you operate at 12.5 ampere, if you give the this current as 12.5 ampere, if you give the voltage such that 12.5 ampere flows, then the wattmeter reading gives you the full rated copper loss. Okay, full rated copper loss. Okay, so this is very important. So the core loss at such a low voltage can be ignored. So these are important lines. Similarly, here also there were some important lines. Since the no load current is limited to 5%, so the copper loss can be neglected and the wattmeter reading does represent the core loss. Okay. So these are the two important statements in OC and SC test. Okay. Now for the SC test, what is the equivalent circuit? So you will see that because the rated voltage, this voltage is very low. For short circuit test, you will find that the voltage is very low. So so here you will see that this will be negligible. Okay. So here this parallel things can be neglected. Okay. So not X rated, this is X1. So this is JX1, R2 dash, JX2 dash. So here you are giving VSC, you are getting ISC, and you are getting PSC. Okay. So this circuit can be written like this. So this is R equivalent. This is JX equivalent. Okay, same things. And same volt BSC, ISC is there. Okay. So how you will get? So basically you will get like this. Okay. So here you will get this like this. Okay. So Z, this magnitude is VSC by ISC. R equivalent is PSC. So this is V square by R is PSC. So it's like this. So this is basically VSC square by PSC is your R equivalent. And you have R equivalent and you have Z equivalent. So X equivalent is nothing but Z square minus R equivalent square. Okay. So this is how you get the parameters. Okay. So let me write this in a more neat way because these are important things. So let me write it in maybe in another color because this is important. Okay. So I try to highlight the important things. Okay. So let me write it in other color and maybe neatly. So this is what? So as I said that Z is VSC by ISC. Okay. Now R equivalent is VSC square by PSC and your X equivalent is root over of Z square minus R equivalent square. Okay. So this is how you basically use the short circuit test values. Okay. Now we will see the efficiency part. As I said that this week we are having open circuit test, short circuit test, and then we are having efficiency of the transformer. Okay. So we'll be discussing now the efficiency. So let us discuss that. So let me put another slide maybe. So this is efficiency. Okay. So efficiency is output by input or output by output plus losses. Okay. because this is like this, right? You give input to a system, you get output, and there are some losses. Okay, so instead of input, because input power may consist of both losses plus output, so I've written it as output plus losses. Or you can also write it as, in terms of input, as input minus losses by input. Okay, either way, like whatever data is given to you, so on the basis of that you can use either this form or this form. Okay, depends on the data which is given. Okay, so you will see that the percentage losses, like, so you will see, it will be said that okay, there is this much of efficiency, or this much percentage, 75%, or like 5% losses is there. So this percentage losses is always in terms of output power. Okay, so percentage losses is always, in questions you will see that is in terms of output power. So that is the thing. Now, as we know that what are the kinds of losses of a transformer? So the losses are, we have seen core loss, which consists of hysteresis loss and eddy current loss. And here we have copper loss. Now, copper loss is proportional to I square R equivalent. Okay, so I square R, we have seen that copper loss is basically I square R loss, or we can write it as V square I square loss, because R can be written as V by I. So no, basically this I can be, so you can replace this and you can get V, so this can be obtained like this also. Okay, so this is in this form. Now this is basically, you will see, proportional to S square. Okay, so it is proportional to KVA square. Okay, now here rated kVA. Okay, rated kVA, if suppose it is full load. Now here the hysteresis loss, so hysteresis loss we have seen is, it is proportional to FBM power n, and eddy current loss is proportional to F square PM square. Okay, these things we have seen in the last class. Okay. Now we will see some important things, okay, in this efficiency. So what is efficiency? Efficiency, as I have said, is output power by output power plus losses. So what is output power? It is written as VI cos phi divided by VI cos phi plus iron loss plus I square R equivalent loss. Okay, so you can, so this is the case. Okay, so but in this case, if cos phi is 1, unity power factor. Okay, so efficiency becomes VI by VI plus PI plus I square R equivalent. Okay, so that is the thing. Now if it is said in the question that it is like X% of the load, okay, it can be 50% or 75% of the full load. It will be generally mentioned that transformer is operating at 75% of full load, 85% of full load, like that. 50 half load, like half load means 50% load or quarter load. Okay, so if it is given like this, so what is your efficiency? Efficiency will become X VI cos phi by X VI cos phi plus PI plus xi whole square R equivalent. Okay. Now we will see one case where we will see what is the situation condition for maximum efficiency. Okay, so for maximum efficiency happens at what load? Okay, what is the load condition of efficiency? So you will see what will happen at the condition of maximum efficiency. So maximum efficiency means ki I can write it like this. Efficiency I can write it as V cos phi by, not writing this X thing. I'm assuming that it is operating at full load. Okay, the efficiency is happening, suppose at full load. Okay, so V cos phi plus Pi by I plus IR equivalent. Okay, so basically this equation only I am writing, but just dividing numerator and denominator by I. Okay, now we have to get the maximum efficiency. Now, when the efficiency will be maximum? When this denominator is minimum. So what is the condition of minima? So the condition of minima is that at what load, right? At what I. So what percentage of load? So as I said that when we have to change the load, we do not change the rated voltage, rated frequency. We just change the current. So that is why the current varies. So at what current or at what load, at what percentage of load this efficiency will occur. So for that we are what you say, derivating it by I. Okay, now we're derivating denominator by I, because if denominator is minimum, then this efficiency is maximum. So the what is the condition of minima or maxima? It is d by di of this denominator as 0. Okay, so if you do that, you will get it as minus Pi by I square plus R equivalent is equal to 0. So what you will get? You will get I square R equivalent is Pi. So basically, you will get the condition, and it is a very important condition. Okay, this is a very important condition, that the copper loss is equal to iron loss. Okay, so this is the condition. So this is what we will see. Okay, so now let us quickly see the questions one by one. So these are most of the things which I have tried to cover, and as we go on solving the questions, things will become more clear. Okay, so let us see the questions one by one. So let us start with this question. So in this question, एक minute. Okay, so let me hide this. Okay. Hmm. So what is this question? So in this question, we are given this data. Okay, now this data is common for the 3 questions which you will be seeing. Okay, so here what is the question? The question is that the full load efficiency. Full load efficiency means when the x is 1. So here you see I have written x, right? So if suppose x is like x% of full load, so if it is 50%, so you will write x as 50 by 100. Similarly, if this is half load. Okay, now if it is full load, then what is x? X is 100%, because 100% is the full load. So 100 by 100. So this will come as 1. Okay, so that is the things. Okay, so these things you should know. Okay, that if it is 50% means you do not write it as 50. Okay, you should write it as 0.5. Okay, so that is one thing which I wanted to mention. Okay, now in this question it is said that the full load efficiency of a 350 kVA transformer is 95%. The maximum efficiency occurs at 75% of the full load. The power factor is 0.8, lagging at all loads. Okay, whether it be full load, half load, 75% load, all loads. So we are supposed to estimate the copper loss at full load. Okay, so we have to estimate the copper loss at full load. Now we are given 2 conditions. One is this and one is the full load condition. Okay, so one is the condition in which this maximum efficiency is occurring, and one is the condition for the full load efficiency. So you remember, you see this, I have written that at maximum efficiency. Okay, so this is the condition of maximum efficiency. Condition of maximum efficiency. Okay, so if it is like VIX is there, so I'll include X also. I think that will make you it more clear. Okay, so I have divided everything by XI. So here we are left with XI. Okay, so you see this is so here also there is X, is it not? So this is XI, this is XI. Now this is X. Here there is X. Okay, so this is what? This is basically x square I square equivalent. So basically x square I square R equivalent is equal to pi. Okay, x can be at any load. 75% load, if maximum efficiency is not necessary to occur at full load. Okay, it can be at any load, like in this question. Okay, so in this question it is said that the maximum efficiency occurs at 75% of the full load. So one equation we have this condition of maximum efficiency, so we will write this condition. Okay, so in this condition we have this x square copper loss is equal to iron loss. So this is basically copper loss at x, what you say, at x load. Okay, is equal to iron loss. So you see this. So you see iron loss we have discussed, right, that the iron loss is constant, whether it be full load, half load, this efficient matlab this power factor, unity power factor, pointed power factor, iron loss is same. We have discussed also, because we generally operate the transformer at rated voltage and rated frequency. If we have to change the condition from full load to half load or 75% load, we generally change the current. Okay, current drawn by the transformer. Voltage and frequency are not disturbed, and as long as we are not disturbing the voltage and frequency, the iron loss remains constant. Okay, so since the iron loss is constant, so for the 75% load and even for the matlab 100% load, the iron loss is same. So that is the thing, right? So for seven, and because this is the condition of maximum efficiency, so for maximum efficiency we know that the iron loss is equal to copper loss at 75% load. So let me write this statement. So iron loss is equal to copper loss at 75% full load. So this is the condition of maximum efficiency. So iron loss, and we know that this I, if this I is rated value, then X is the percentage of full load. So this becomes X square. So this becomes, this also can be written as X square full load copper loss is equal to Pi, because I square R equivalent is the full load and there is X square terms. So copper loss at X percentage load is equal to X square I square R equivalent is also equal to X square of full load copper loss. Okay, so I will be writing it as X square. So X is 75%. So 75% of the full load copper loss. Is this clear? Whatever I have written, is this clear? Is there any doubt here? Okay. So I hope there is no doubt. So if you have any doubt, please stop me. Okay. So this is what I have written. So this is one condition. Okay. Now what is the another condition? So the another condition which we know is that the, so this is the efficiency at full load. So what is the efficiency at full load? So we can write it as Vi cos phi divided by Vi cos phi plus iron loss plus, because it is full load, so it is rated copper loss. So rated copper loss is 95%. Okay, so this is 95%. Now Vi is what? Vi is 350 kVA. So this is 350 into 0.8. Okay, 0.8, because it is said that the power factor is common for all loads, same power factor. Okay, 0.8 divided by 350 into 0.8. Okay, this is in kilowatt. Okay, this is this, because I'm not writing into 10 power 3, so this is kilowatt, plus iron loss plus rated copper loss is 0.95. Okay, एक minute. So if you rearrange this, then you will get it like this. Okay, so this will come out to be in this form. Okay, I'm not writing it because there is no space, so you will see that it will come out to be in this form. If I cross multiply it and I properly take the these on the this iron loss plus rated copper loss on the left hand side, then you will get it like this. Okay, so you have this one equation, you have the second equation. Okay, and iron loss is iron loss and rated this, so this second equation is also in terms of iron loss and rated copper loss, and first equation is also in terms of iron loss plus rated copper loss. So you have two unknowns, two equations. So if you can solve it, you can get the rated copper loss. Okay, so this is how you solve the question. So is there any doubt in this question? Okay, so if you have any doubt, please ask. Okay, now I'm going to the next question. Now in this question, that is the continuation, this data. So we have to estimate the iron loss. So you see, it is it is like these are all related. So you see, we have calculated that the iron, we have this equation, right? The second equation, that iron loss is 75%. This is at maximum efficiency is x square into rated copper loss, where x can be percentage loading at which maximum efficiency is happening. So if we use this what you say equation, because we have solved for the rated copper loss or full load copper loss, so we can get the iron loss for the next question. So for the iron loss for the next question, you just put the value of rated copper loss which you have obtained from this question directly here, you will get the iron loss. Okay, so this is a very simple thing, just a continuation of that previous question. Okay, now in this question we have to estimate the percentage efficiency at the half load. So you remember this formula which I have written here. Okay, so here x is 0.5 because this is half load, so x has to be 0.5. Okay, so let us now write the things. Remember, whether it be half load, full load, or 75% load, the power factor is 0.8. Okay, at all. They have said that power factor you have to take 0.8 at all loads. Okay, so what is the efficiency here? So efficiency is x vi cos phi by x vi cos phi plus iron loss plus x square full load copper loss. So what is x? X, because we have to do it at half load, so x you have to take as 0.5. Okay, so this is what 0.5. Vi is 350 kVA, so write it as 350 kVA. Cos phi is 0.8 for all loads, so 0.8. Similarly, down also you write it. So here also 0.5 into 350 into 10 power 3 into 0.8, plus iron loss is constant, whether it be half load, full load, 75% load. Okay, so iron loss we have determined from this previous question, so we will write for this question also, it will remain the same. Okay, so we will just write it as 5305 plus 0.5% of full load copper loss. Now full load copper loss we have from the first question, 9431. Okay, so this is just 9431. 31.57. So if you solve it, you can you will get it as 94.8%. Okay. So as I said that this assignment is easy if you understand these things. Okay. If you understand these equations and how you are writing it, what is the meaning of X here, what you will do if there is half load, full load, what you will do if there is power factor change, what happens to the iron loss. So if you know these things, it is just the manipulation of this, what you say, equation. Okay. It's easy. This assignment is not tough. So now we go to the fourth question. Now in the fourth question, now we will are seeing the OC test and SC test. Now they are combining the OC test, SC test and efficiency questions. Okay. So here they are saying that the OC test is performed from, because we have discussed that it is performed on the LV side. So this is performed at this voltage. So you see we are performing the, so this is the transformer rating. Okay. Transformer is rated at 500 kVA, 33 kilovolt, 22 kilovolt. Okay. Now we are performing the OC test on the 22 kV side. Ek minute, let me admit the person. Okay, so we are performing the OC test on the, you see, low voltage side. And you see, because this is at the same voltage rating of 2200 volt, so you see we are performing the OC test at the rated value. So because we are performing the OC test at the rated voltage, which can be low voltage or high voltage, because they did it on low voltage side, so they have written it as 2200. So this power represents what? This power represents core loss. We have discussed this. Okay, that if we perform the OC test at the rated voltage, rated frequency, because frequency in the transformer is generally not changed, it is operated at the rated frequency only, otherwise there will be flux saturation problems and all. So we are performing it at rated voltage and rated frequency, means this power which is taken at from the OC test represents the core loss. See, we have discussed this very earlier. Okay, so you can see that we have written also. So since low load current is limited to this, so the wattmeter reading in OC test represents the core loss. Okay, if you are doing it at the rated value. Okay, so that is the thing. So remember, if you do it at the rated value. Similarly, copper loss, if you do the SC test, what you say, at the rated current. Okay, so this is at rated current, then the wattmeter reading will represent full load copper loss. Okay, so here also if you do it at the, what you say, rated voltage. Okay, so this has to be at the rated voltage, otherwise this will not be the what you say, copper loss, core loss. Okay, similarly for the copper loss. So coming back to this question, now here you see this is the thing. Now what is the next statement? The next statement is that the SC test is performed from the high voltage side. Okay, and this voltage and this current. Now let us try to find the rated high voltage side current. So what is the rated high voltage side current? It is 500 kVA by, what is the high voltage rating? This is 33 kilovolt. So you will get it as some current. So if you do that, you will get it as 15.15 ampere. Okay, so you get it as 15.15 ampere. So this, you can see that the short circuit test is not done at the rated value. So these things are very important. Okay, you should not be like, acha, this is the SC test, so this represents the full load copper loss. No, you see the current and voltage also, okay, at which the OC and SC test is being done, because this current is not the rated current. So you see this what you say, this reading is not the full load copper loss. Okay, so don't get confused. Okay, so you should know each and every point very clearly, otherwise you will do mistakes. Okay, now what we have to do, we have to determine the percentage efficiency at full load and 0.75 power factor. Okay, so as we know, what is the formula of efficiency? Efficiency is, because it is full load, so X is 1. Okay, so XVI cos phi by XVI cos phi plus iron loss plus X square, uh, basically full load copper loss. Okay, because this is we have to determine the efficiency at full load only. So X you have to take as 1, VI you have to take it as 500 kVA, Okay, so this is 500 kVA. Cos phi is said to be taken as 0.75. And see, iron loss also we know from the OC test. Okay, so iron loss is 6 kilowatt. Okay, so this is the iron loss. Now, what we need to determine? We need to determine the full load copper loss. But you see the copper loss which we are getting it at 10 ampere. Okay, so this is the copper loss at 10 ampere. So copper loss at 10 ampere is 6.78 kilowatt. So what will happen to copper loss at 15.15 ampere or rated current? So it will come out to be 6, because copper loss is proportional to current, so it will be multiplied by this 15.15 square divided by 10 square. So copper loss at rated current or full load current will come out to be, okay, so you know all this data, you can use it in this equation, so you will get the value. Okay, so this is how you solve for this question. Okay, so now we go to the next question. Now in this next question, yes, here. Okay, so why we are squaring the current values is, if you will see, so copper loss, if you see, what is the copper loss? Copper loss is proportional to I square, is it not? So because it is proportional to I square, now we know that the copper loss at, suppose we in this question, just remember this, okay, that it is proportional to I square. Now we know that copper loss is what? Copper loss at 10 ampere. So it is copper loss at 10 ampere is 6.78 kilowatt. Okay. एक minute, wait for some time. एक minute, wait for some time. I'm just coming back. Okay. Wait. Okay. So as I was saying that here you see the copper loss at 10 ampere. Where is it? Okay. So copper loss at this 10 ampere is what? This is 6.78 kilowatt as per this question. Okay, this is 6.78 kilowatt. And we know from that that it is what? 10 square R equivalent. Now copper loss at rated current 15.15 ampere will be what? It is proportional to 15.15 square R equivalent. Okay, so if I divide, so I have 6.78 is equal to 10 square R equivalent by some x value which I want to determine. It is 15.15 square R equivalent. So R equivalent will get cancelled. So x will be what? X will be 15.15 square into 6.78 kilowatt by 10 square. Is it now clear? Okay, like this. Iron rated voltage, yes, because this is 2200. You see the transformer parameter is what? It is 33 kV by 22 kV. Now we are doing OC test at 22 kV itself. So as I discussed in the very beginning theory, that if you perform the OC test at rated voltage, rated frequency, the what you say, the power, this wattmeter reading indicates the core loss. Okay, so that is why we have taken that it as the what you say, core loss. Okay, so excuse, what did you say? Just say it again. Okay. See, in the first of all, in the SC test, you do it at rated current. Now, when you do it at the rated current, like what you do is you short circuit the other winding. So you will see that the voltage requirement will not be 2200. Okay. So voltage requirement will be very less because for, see, I have discussed this thing. Okay. So here, when what happens is, if you do the short circuiting here, so because it is short circuited, so with very small voltage only you can get the rated current, and that voltage is like 5 to 10% of the rated value. Now you can say that you can do it on the low voltage side or the high voltage side, if that is what you were trying to say. Okay, you can do it on either side, but generally it is done on the high voltage side because the current requirement is low. Okay, so here if it is 15.15 ampere, on that side 2200 volt side, it will be like 3 by 2 times more, 1.5 times more. Okay, so if it is said, if it is said that this short circuit test is done on the low voltage side, if they have somehow written it, generally they will not write it because they generally prefer to write it in this practice only. But if somehow for some question, for some theory question, they have written it, they are doing it on the low voltage side, then you have to calculate the rated current on the low voltage side. Okay, which will be 3 by 2 times of this 15.15 ampere. Okay. Okay. Hmm. It's not related to the voltage. Okay. AC test. Okay. Now, for the same question, we are estimating the efficiency at half load and unity power factor. Very simple. We know we have everything with us, right? So as per this formula, it is what? XVI cos phi by XVI cos phi plus this iron loss plus x square times of rated or full load copper loss. Okay, now what is x? Because this is half load, so you have to take x as 0.5, and cos phi is unity, so you have power factor, so you have to take cos phi as 1. Okay, so here you have all the things available with you. Okay, so here is what this is: x is 0.5. This you do not see, this is wrong. Okay, x is 0.5 into this vi is 500 kVA, so you write it as 500 into 10 power 3, cos phi is 1. Then again this is 0.5 into vi, which is 500 kVA, into cos phi is this. This iron loss, we know this is at rated voltage we get iron loss, so this is 6 kilowatt plus x square. X square is 0.5 square, and we have obtained the full load copper loss in the previous question. So full load copper loss in the previous question we have obtained as this value. Okay, so you will write x square into this much value. So this will be 1556.4.73. So if you solve this, you will get some value which is not this value, obviously. Okay, so you can solve it in this way. Okay, now we go to the next question. Now in the next question, this is the same data. Now we have to determine the kVA output at which maximum efficiency occurs. Okay. Now this we have seen the condition, right? So what is the condition of maximum efficiency? So the condition of maximum efficiency from of all this derivation is that if you have to determine the value of x, so it is what? X square into full load copper loss should be equal to iron loss. Okay. So from the previous two questions, we have iron loss also and full load copper loss also. So we can just use this formula directly. Okay. So this is what? So as I said that the condition of maximum efficiency is that x square full load copper loss is equal to iron loss. Okay. Where x is the what you say, how much is the, like, whether it is 50 per half loaded or half load rated, full, what is 75% rated, whatever. Okay, so it can be half load or anything. Okay, etc. So this is what it will come out to be. So you can just solve this. So we have iron loss. So iron loss is this 6000. So this is 6000 x square into, we have to determine the kVA. Okay, so what will be the kVA? So first we determine the value of x first, so we will see how to calculate the kVA after that. Okay, so this is what, so we have seen from this question, we have calculated the full load copper loss from this question. So it is 15564.738. Okay, so this is 15564.738. So 64.738. So if you do this, you can get the value of x. Okay. Hello, mummy. हेलो, मेरा भी क्लास चल रहा है, आपसे बाद में बात करती हूँ। ठीक है, so that is how you can determine this. So if you determine this, you will get the value of x. Now what about the kVA rating? So for kVA, kVA is what? Operating voltage. Okay, voltage into operating current. So we generally operate at the rated voltage. ठीक है, so this is generally operated at rated voltage. So we have seen, right, because we generally operate the what you say, actual things on the, if we suppose, if we have to change the loading, we change the what you say current rating, not the voltage rating. Okay, because if we change the voltage rating, then what happens is that we can have V by F issues, and then there will be flux saturation issues. Okay, so operating voltage is rated voltage, so this is rated voltage. And what about operating current? So we will be operating at this x times of current, so this will be x times of rated current. So this is what, x times of rated voltage into rated current. So you can see that this is what, x times of this rated VI rating. So this is x times of 500 kVA. Okay. So this is how you can find at what percent, at what is the kVA output. Okay, what is the kVA output at which efficiency occurs. Okay, so this is, in this way you can calculate this value of this. So you will get this, that value as this value. Okay, so is there any doubt till now? Okay. So now let us go to this. So this data is for the last 4 questions. They're very simple questions. Okay, if you understand these things very clearly, then these questions are very easy. Okay, you can do all sorts of questions in this assignment. Okay, in whatever is your current assignment, you can solve it. Okay, now what is the question? Now here what we are doing is that we are performing the OC test on the low voltage side. So you see we are performing it at 330 volt only. Just always see for the low volt open circuit test whether the voltage is rated or not. So this is rated voltage. Okay, so this is 330 volt is also the rating. So this is, so this thing gives you the iron loss. Okay, just keep it in mind. If it is required somewhere in the questions, you can just keep it in mind. Okay, similarly, SC test is performed on the from the HV side with the LV side shorted. So this is the current. Now you can find out what is the HV side current. So this will be 100 kVA. Okay, by 440. So this will be how much? So this will be let me calculate in the calculator. Yes, so not the value, right? Not the, so maybe they have taken it matlab somewhere near. Okay, so but it is okay. But generally this you will see that in these questions. So you can keep it in mind that it is at 22.7, which is nearby that, but it is still not the rated copper loss. Okay, it is at some 97 or some percentage of the rated copper loss. Okay, now coming back here, now this is the impedances. Now what we have to do, we have to estimate the parameters of the equivalent circuit. Okay, So this information is not that much important here, but it is a good practice to, so it will keep you, what you say, in a habit. Okay, this is a good habit to note down these things. Okay, now we have to what determine, we have to determine the equivalent winding resistance Re. And remember, this equivalent circuit is referred to the HV side. HV side means 4.4 kV side. Okay, so they have referred it on the high voltage side. That is why they have written with the superscript HV on all the parameters. Okay, now what we have to determine, we have to determine this REHV. Okay, so how to determine this REHV, I have discussed this here. Okay, so this one basically gives you the so because this is VSC and ISC is on the HV side only, so this is on the HV side. So these values will give you the Z, R equivalent, X equivalent referred to the HV side. Whereas these values, because we are doing it on OC test on the low voltage side, so these values will give you the values referred to the LV side. Okay. We were here. So because we want, so as we have seen that the short circuit test will give us the value referred to the HV side only, and we want to get the values on HV side, then we can directly just calculate and get the answer. So as I have said that what is the value of Re? Re is nothing but this P short circuit by I short circuit square. So you can just do this and get the value of Re. Very straightforward. Okay. 23 squared, so you can get the value of Re, which is already referred to the high voltage side. And because they're asking it on the high voltage side only with this superscript HV referred to HV side, so this you do not need to transfer anywhere. You do not need to transfer it again to low voltage side or something. If they would have asked you refer to the low voltage side, then whatever value you are calculating, you have to multiply the proper transformation ratio so that you transfer it to the low voltage side. Okay, but it's because this is on the high voltage side itself, you can directly write this. Okay, now we have to determine the XE high voltage on refer to the high voltage side, because this is also we get from the short circuit test only. So directly we get it on already referred to the high voltage side, because short circuit test is done on the high voltage side here. Okay, so so what is, how you can get it, you can get Z equivalent as this VSC by ISC, which is 120 by 23, and R E, which you have already what you say calculated in the previous question as 2.45. Okay, so this is 2.45. Now what is XE? XE is nothing but ZE square minus RE square. Okay, so that is what you have to do. You do this, you will get your answer already referred to the HV side, because this by default gives the short circuit test is done on the HV side, and by default using the values here will give you VSC and using VSC and ISC which are available on the HV side gives you parameters referred to the HV side. Okay, now we come to this. We have to determine the core loss resistance referred to the HV side. Now we understand that the OC test, which gives us these parallel parameters, are done on the LV side. So if we use the formulas as per that, so what we have to do is we have to again transfer it by multiplying it by the proper multiplication factor and transfer it to the HV side. Okay, so let us first use this data which are available on the LV side, and then after using the data, whatever resistance we get, that we can transfer to the HV side by properly multiplying the multiplication factor. Okay, so as I have again discussed in the previous slides, you can see so how we can calculate the what you say this R0. R0 is like, so you can calculate R0 like this. We have seen these things. Okay, कहाँ गया? हाँ. So like this, you can do it as VOC square by POC directly. Okay, so if you do it VOC square by POC, you will get it referred to the LV side. Now you have to multiply it properly by a proper multiplication factor, which we have seen earlier in the earlier classes, that we have to multiply it by the proper voltage ratio, because we are moving this from the LV side to the HV side. So from LV side to the HV side, we are moving this R0 so that it becomes R0 HV. What we have to do is we have to multiply it by this. Okay. You can see it in the previous class discussions. I have discussed how this ratio comes out. Okay. So if you do that, you can get the value referred to the high voltage side. Okay. So they have also done it in the similar way. You can also do it like that. Okay. Now we'll see the last question. Now in the last question, we have to determine this XM referred to the HV side. Now be very careful. Do not be like, acha, if I do V by I, then I'll get Z, then again Z minus R square I'll do, then I'll get X. No, this is a parallel combination. You cannot do it like that. Okay. So you cannot do it like that because this is a parallel combination. So you have to use the formula which I have written very specifically. Okay. So, okay. So let me go to that formula. So where is this formula? So see, this is how you have to do. First, you can determine this phi 0. After determining the phi 0, you can do this XMS P0 by 10 phi 0. Okay, you have to do this judiciously because this is valid for the parallel combination. Okay, you cannot do this way. You cannot do it this way because this is for the series combination. Okay, not for the parallel. So let us do it in this way. So phi 0 is cos inverse PO by VOC IOC. And then what is X? X is nothing but, I guess, what was X? Okay, X was PC by 10 phi 0. Okay, like that. So if you do that, you can get that. So I think PC is in the per unit. Okay. So what you can do is that if you that actually that formula is in per unit. Okay. So you have to be cautious. So once you have gotten this thing, so what is this? So or maybe you can do it in this way also. Okay. Or you so maybe you can do it in per unit also like this. You can just divide this P0. So this P0 is what? 1600 watt. So this 1600 watt, you can divide it by 100 kVA. So you can write P0 per unit, okay, as 1600 divided by 100 kVA. Okay, so if you do this, you will get P0 per unit. And this is X0 per unit. Now, after getting this X0 per unit, you can multiply it by the what you say, this Z base. And what is this Z base? Z base on this low voltage side is what? On the low voltage side is V square by P. So this is 330 square by 100 kVA. Okay, you can do this. So you can get it in this way, but it is referred to the LV side. Okay, if you multiply the Z base on of the HV side, then you will get the X0 referred to the HV side. Now what is this Z base on the HV side? It is 330, this is 4400 square by 100 into 10 power 3. You can do it like this or you can do it like this. So here what they did was they are actually so they know that okay, this because this current, this overall current is like this, which is the parallel combination of this R0 and JXM. So they are saying ki acha, this current is divided into this part and this part. Now this so here so you can do it in this way, okay, but I prefer to do it in this way. Okay, so you can see whatever is convenient to you. I cannot explain what is their method though. Let me try to see what they're doing. So magnetizing current referred to the LV side. Okay, so they are first of all doing magnetizing current calculation. So magnetizing current is here. So they are saying, okay, so they are saying that this 13 ampere hole is going on in this. Okay, like that they are saying. Okay, I actually do not know how they are saying this. Okay, So, okay, I understand like that. Okay, so what they are saying is that V by I, okay, is Z, and then, okay, I'll maybe tell you what they are doing in the next class. Okay, but you can do it in this way also. You will get the same answer. Okay, I'll try to tell you what is this. Okay, what they are trying to do. Okay. Actually, I'm not feeling that well also. I'm having little bit cough cold. So I'll think about it and tell you in the next class. But this is the last question of this assignment. Okay. So that is it for this week. We will be meeting again in the next week with new things. So this is what we discussed in this whole class: open circuit test, short circuit test, and efficiency of transformer. We have seen the what is this OC test and where it is performed, why it is performed at rated voltage, rated frequency. It gives us core loss, which is treated as constant. Okay, then OC test, how it represents the core loss only fully, why not it does not have any copper loss. Okay, all these things I've discussed, and then how to use these formulas. Okay, then we have discussed the SC test. Then in the SC test we have discussed this, what you say, where it is performed, why it is performed at the rated current. Okay, and then why we do not get any, what you say, core loss component when we get the copper, why we only get the copper loss component when we measure the power, and how to see these things. Okay, then we have seen the efficiency, and then we have seen the how, what is the condition of maximum efficiency and how to apply this efficiency formula. Okay, so this is there in this week, and you can solve most of the questions if you understand this. Okay, all this discussion, if you understand, you can solve the question. So that is it. If you do not have any doubts, you can leave. Okay, if you do not have any doubts, you can leave. So the class, yes, I'll share this PDF, and I'll upload both. Okay, yes, I'll upload both in PDF as well as PPT, Akash. Okay, so that is it. So you can leave. I That is it for today's class. You can see the recorded lectures. People who like joined late or came late, you can see the recorded lectures. Okay, I'll upload the video and PDF both. Okay then. Sure. Thank you. Okay. Okay then. Thank you. You can leave. Thank you. If you do not have any doubt, sure. Thank you. Okay then. Okay. Hmm. Okay. Okay then. So I'm leaving if there is no doubts. Okay. I'll upload these things today only. Okay then. Okay. I'm stopping the presentation. Let's meet again the next week. Okay then. Okay. Okay.